So I'm now starting to talk about what is in the script, and the first thing we find there are issues of problems. That's a nice color. Problems. Let's do it black. Problems, algorithms, and programs. And a way to get started in programming is first to think about what programming and everything is actually about. And what I find helpful in this regard, specifically if you're in cognitive neuroscience, are the so-called MAR levels. Does anyone know what MAR levels are? So has anyone heard these before?
I just heard of it on the YouTube.
On YouTube. Okay. So they are the typical, it's a typical cognitive science, cognitive neuroscience thing. So David Marr was a psychologist in the 70s and 80s, and he thought about how to analyze the visual system, and he came up with these 3 levels of description. So the first level being the computational level. It's a little bit of a problem in terms of the name, because what he means by that is the problem specification. Yeah. So if you want to program something, or if you're thinking about what the brain does, the first thing you in a way need to think about is what the actual problem is. Yeah, because you cannot just start writing code without first thinking about what you're actually trying to do. I mean, it's as trivial as that, but it's important to keep that in mind. And the better you can specify what your problem is, the easier it's actually to find a method to solve it. And one important thing in programming and in general scientific projects and so on is to be able to break bigger problems into smaller problems, which you usually do in terms of problem specification. So one example would be you want to do an fMRI analysis using nylon. That's your big problem specification, but now you need to be more precise in terms of what the actual components of this problem are. So first of all, what is fMRI data? How do I get fMRI data? What are the details of this fMRI data? And then in terms of data analysis, what does a fMRI data analysis entail? What are the parts of a fMRI data analysis? And then if you add the parts of a fMRI data analysis, for example, you can distinguish pre-processing and statistical analysis. Then in pre-processing, you might have as a first thing alignment or motion correction. So then you have something, with your problem specification, you are at a level where you can actually start talking about algorithms that you want to use to do that. And these algorithms then in this case would be maybe some functions in your nylon toolbox. So it's very important, and specifically if you want to succeed in terms of doing projects and finishing projects, it's always important to constantly rethink what are actually the problems that we want to address. And in terms of the brain, this is kind of the task that the brain is trying to solve. So that's kind of a global and problem-centered view. And then there is what Mark called the algorithmic level. And that's about the problem solution method, if you want, or let's just call it problem solution pathway, something that is not algorithm but the same thing, problem solution method maybe. So this then really refers to algorithms, and algorithms, and this is the important thing here, algorithms are not necessarily only things that are implemented in computers. I mean, that's the whole point of doing computational behavioral modeling, for example, that you talk about algorithms that can also be implemented in brains. But they need to be specified in terms of algorithms. So what are key features of algorithms? Well, key features of algorithms are finite description. So a typical example of an algorithm is a recipe for, I don't know, baking a cake. So this recipe or recipes for cooking, they are finite. So usually they fit on one page. If they would be infinite and you always have to do something else and then something else and then something else, you will never have your cake. So they need to be finite. There needs to be a finite description. Then they need to be what is referred to as effective. That means, or effectivity, maybe I should write. That means you can actually do everything that the algorithm prescribes. So if you have a recipe and at one point it says that you now, I don't know, the only thing that comes to my mind is now you should add some uranium to your cake. You will not be able to do that because you will not be able to acquire uranium unless you are, I don't know, working in a what's it called, atomic plant. So all the things that are in the algorithm, you need to be able to carry out them. Otherwise, it's not a useful algorithm. It's not, wouldn't even be an algorithm. So if you also, another thing would be you have an algorithm like a recipe, and then it says, and then you need to do some magic, and then the cake is done. So that's something you can't do. It's not an algorithm. It's useless. It's fantasy. And then something that is in a way related to finite description, but not necessarily, because you can also give a finite description of something that never terminates. So I don't know, bake the cake until I don't know, until all electricity is gone or something. It's a finite description in a way. In a way, it will also be effective. So if you have to wait until the end of the world and all this electricity collapses or whatever, yeah, but you want it to terminate. I mean, this is of course something that is more reminiscent of while loop. So you wouldn't call an infinite while loop. This is where this is coming from. You wouldn't call an infinite while loop in an algorithm. And then another thing is that it's deterministic, although one can actually start discussing that. So the idea would be that if you apply this algorithm in a given setting, then it's deterministic what you get out of it. But that depends a little bit. That's all. So I mean, this is in a way, if you want, it's a little bit of an old school definition of an algorithm. If you think, for example, about function minimalization, like this morning. So the general way to think about these as algorithms are that if you have a certain problem, they give you the same solution, but there have been, of course, also developments in kind of probabilistic optimization, and there the solutions might actually not be deterministic. Yeah, so it's in principle an algorithm, and what I take from these four notions is that an algorithm should be like a recipe. If it's not like a recipe but more complex than a recipe, then it's not an algorithm. Yeah, and I think the recipe analogy is quite good for algorithms, because algorithms in principle are really simple. They are just a sequence of steps that you need to carry out, and if you have carried out these steps, then you have your result, then you have your cake. Yeah, of course things can go wrong and so on, and you might make mistakes, and then the cake is not as awesome as it should be. But in principle, an algorithm is not something highly complex and that nobody can understand, but it's like a recipe. Do this, and this, and then you get something. Whether certain algorithms then really solve the problem, that's another question, but at least they do something. So that's the algorithmic level by Ma, and then Ma finally talks about the implementational level, and this is really the question then for us as cognitive computational neuroscience or whatever. The question is this algorithm implemented in a computer? And in programming, we of course will always be interested in computer implementations of algorithm or the brain. Another way, of course, you can talk about this is if you focus on computer, whether it's implemented in Matlab, so the Matlab implementation, or Python, right? So different programming languages are also different, can implement the same algorithms, but then there's a difference in terms of the implementation level. Yeah, so this is kind of the very big picture, and introducing a little bit of Ma levels, which is always helpful if you think about cognitive neuroscience. Yeah, so if you are interested in cognitive neuroscience, which in a way I hope you are, of course, then you should always address your cognitive neuroscience problems from my perspective in terms of first thinking about what is the problem that the brain tries to solve. So basically the task that we are talking about, then what are solution strategies to do that, and yes, from a cognitive science perspective, these are then algorithms, usually also algorithms that relate to numbers. That's the current metaphor, what the brain is doing. And then the last question is, so this you can do basically purely on behavior, for example, behavioral data. But then the last question is, how is this actually implemented in the brain? And apparently, really, the whiteboard at one point gets reset to blank in Cisco WebEx because the stuff went away again. But we were almost done. Good. So that are Ma levels, and the idea of algorithms as recipes, essentially. Now, of course, we are here specifically interested in the implementation in computers, so we want to talk about programming. And programming, if you want, you can call this, you can call programming the implementation, or you can call a program, let's do it like this, this is what I was looking for. You can call a program an algorithm which can be performed, sorry for writing this out, which can be performed by a computer. Yeah, so if you want to learn programming, you want to be able to specify algorithms that can be performed by computers. And so you need to be able to tell a computer what the computer is supposed to do. And of course, this has not been done throughout mankind, but these kind of electrical machines that can compute haven't been around forever, but really started like after the Second World War. So maybe you have seen this stuff on this movie about Turing and the Turing machine, and how he kind of developed a sort of computer to decode what Enigma, so this machine by the Nazis that kind of encrypted messages, how he solved this with kind of developing first computers. So Turing as kind of one of the big inspirations for developing computers. And this, of course, was kind of Second World War. And after that, of course, computers started to be developed more and more. And of course, you all know that the big kind of really the rise of the personal computer as something that is really being used only started in the 80s. And of course, so with Microsoft and Apple, so you know that, and that kind of that computers really became things that everybody has at home. That's more 1990s, so it's really not that old. And and that computers are essentially everywhere, and you have them in your cell phone. Of course, you know that this is all only the last 20 years. So, but all of this, of course, relates to programming. And in the early days, programming and this kind of evolvement of the computer also brought with it kind of a evolution of programming languages. And the thing is that, of course, computers, the ones that we use now, the computers have processors, which are physical entities which work with electricity, and essentially are based on switches, namely on-off switches. Which then lend themselves to a binary code. Yeah, so in a computer you can turn on a switch so that electricity flows, and you can turn it off. So you the only thing, and this is what's also important, the only thing that a processor of a computer understands is kind of this electricity flows, electricity doesn't flow. And with this very basic thing, the computer then needs to do things. Now, in terms of telling the computer what it needs to do, what things started out with are so-called machine languages. So that's kind of 1950s, maybe even earlier. And these kind of machine languages that tell computer what to do are binary code. Yeah, so they kind of are sequences of zeros and ones, and this means something to a processor. So this might mean something to a processor, whatever exactly it means. And the problem in a way with machine languages, and for examples could be write or save something somewhere in computer memory, or add two things that are stored at this point in computer memory with at this point in computer memory, and then do a very simple addition or multiplication. Or a logical operation. So this needs to be expressed in this machine language, and if you program today, what you program in your what is then called a high-level programming language is still translated into this, so that somehow your processor knows what it's supposed to do, but you don't have to understand the language of the machine. What then, because we are now using a more high-level programming languages. So what then followed are these kind of assembler languages, which I guess now making some guesses here. So 60s stuff. Maybe even also 50s, which also which kind of go into a direction of a language that we can understand, but still look kind of weird and not really nice from a human perspective. So these would be this would be like code like this. So move some element that is stored in computer memory from this point to this point. This is called what assembler languages. But what really then only became or where programming really started is then with higher programming languages. And with this I mean stuff like for example Fortran, COBOL, and that's do you see the whiteboard? Okay. There's nothing on it. Interesting. I had a lot of notes on there. Well, you can see them if you watch the video, the notes, but then so do you see some whiteboard? You can scroll on the whiteboard. Maybe scroll a little bit around. Okay, so people have found the whiteboard again. Good. Maybe you need to scroll on your own thing. Yeah, it will be uploaded, so of course I'm recording it. So we were at this point where we are kind of in the 1970s, where more higher programming languages like Fortran, which is good for matrix calculations, and COBOL came across. COBOL actually recently, does anyone know why COBOL recently became of interest again? No. So the thing is, now with Corona, they needed in the US, they needed to change a lot of things in terms of how they give away this money to help people, and they actually have to kind of the administrative or the government entities that are related to unemployment and so on, they are running on COBOL stuff because that was used for business administration. And now they needed to change a lot of this to implement these things that came with the Corona help packages that were recently announced, and hence people needed COBOL programmers, because this code has been running and doing its stuff since the 1970s, and nobody knows how to program COBOL anymore. But this is that I recently came across COBOL again. What really, of course, has been the main thing in terms of programming languages, yeah, definitely since the 80s, are things like C, C++, and Java. And these are the programming languages which are called higher programming languages. So you might also call them third generation. I think that's not wrong to say that. So third generation languages, and they are more, the main thing is that they are human readable. So they have these typical statements that you set some variable to something, and then you say, then you write a for loop, something, oops. Well, it can do certain things, but not necessarily what it's supposed to do. So then things like for loops, so for e like 1 to n, do something. These kind of statements that you are familiar with from programming languages, they came with this third generation language. This is, I think, why Python, because it obviously builds on C, and C++ is also sometimes then called a fourth generation language. So this so this is C, C++, Java. So this is basically then 1980s and 90s programming, and as we will then see later, 1990s and then basically up to now, simplified higher programming languages, so like Python, then came around and are being used today. So is there something that somebody would like to add in terms of the development of programming languages and where we currently are? No.
As far as I know, Fortran is the precursor of Matlab too. The founder of Fortran is the founder of Matlab too.
Yeah, that's definitely the case. So the like Python, Matlab was also originally developed in teaching to have. I think that's exactly the sentence you find somewhere in the Matlab history, to make it easier for students to interact with Fortran libraries for matrix calculation. This is why Matlab was developed, so in teaching. But then, of course, Matlab was turned into a commercial product, and they make money with that. But it's a good product. Good. So this is kind of a very brief overview about programming languages. The thing with Python, and this is also something that I, when studying it, Python is always developed a little bit in contrast to C and C++, these kind of languages, and trying to make things simpler. If you start out programming in Python, then of course you haven't really had the problems or the issues that people had with C. And then it's not that easy to appreciate why this is now awesome, because it's just how things are. So it helps even if you are not interested, if you don't want to program in C, maybe at one point look a little bit into C programming to understand where also Python and this philosophy of Python is coming from. Personally, I've only done one course in C on my own, or C++ once, but I never did a project in C++, because in the end it never really was necessary. At one point I thought I want to implement something that was taking too long in Matlab in C++, but then that never happened. So yeah, have a look at C code if you're interested in that. Now the last thing in terms of this introductory stuff that I want to introduce are programming paradigms. So how do I scroll now? Apparently you can, there's a limit to this whiteboard. It's not an endless whiteboard. It stops at one point. Now then go to whiteboard 2. So what is important and what you should also have heard are different programming paradigms. What we will deal with, namely Python, Matlab, and also C, they are definitely imperative programming paradigms. What that means is that you tell in a program, you tell the computer by means of statements what the computer is supposed to do, and they work on, and the computer works on your statements line by line. So you tell them, you tell the computer X, you assign, for example, a number to a variable, and that's a statement, and then the computer does this, and then it goes to the next line and does this, and you tell it what to do. The difference, and what also has been of interest to artificial intelligence researchers, is what is called declarative programming, where I hardly actually know anything about. Actually, I don't know anything about this. And there are two kind of things: logical programming and functional programming. And the things that are associated with that is Lisp. So Lisp is also I think in cognitive science of some interest to some people. The thing is, this is kind of this declarative programming. The idea is that you don't tell the computer step by step what it's supposed to do, but the computer figures it out by itself. So this is, of course, from an AI perspective, that's fancy, and the computer figures something out. But in a way, as I understand it, is that it's essentially trying to find proofs of logical propositions. I have no idea. Has anyone ever done something? I think the Prolog is also an example of that, if I'm not mistaken. Yeah. So logical programming, Prolog. Has anyone ever done something in Prolog? think in
Not done Prolog, but I've done some answer set programming in a language called Klingo, and that's basically like you define constraints, and then the program kind of generates all the possible outcomes based on the constraints that you've defined.
Okay, and is it
I
fun?
guess that's the easiest. Sorry?
Is it fun? Does it do anything useful?
Yeah, I think it's particularly useful for like logistics. So for instance, Amazon in their planning of their routes and where they can put certain inventories and things, they're using these kinds of programming languages because basically once you define the constraints, then you allow for the generation of all the possible outcomes. So if you define your constraints in a sufficient way, then you only have the sort of possible outcomes. It also works for programming elevators, for instance, in an optimized manner.
Yeah, okay, I see that a little bit. So that's a good point. So I would so programming elevators and doing kind of these logistics. I would understand them. So I would understand this then as implementations of constraint optimization methods that maybe come with their own programming language.
Yeah, could be. I just know that these languages are used for that, but apart from that, I'm not. I'm sure you can do it in other languages. I just think that that's their primary use.
But it makes some sense. So if you always have these kind of constraint optimization problems, then why not use a language that is really devoted to solving these constraint optimization sets? I think Prolog is also for robotics. I know that the cognitive science people in Osnabrück, they apparently always learn some Prolog. Okay. What we are dealing with is imperative programming, so that's definitely what I know more about. And in in imperative programming, so where you write statements and then the computer works on them line by line, one can distinguish two kind of ways of doing things, and one being procedural programming, which in a way keeps data and functions separate. So what this essentially, what I'm referring to there here is that you have like variables which are only some data, and then you might apply a certain function to that. So you call some kind of function. Let's call this function, because we are in programming now, let's call it myFung. And you call that on X, and this is kind of typical procedural programming. You can also functions, so that you apply functions to data. That's a typical thing of procedural programming. Procedures in C and functions in Matlab and functions in Python. That's essentially all the same thing, of course, with the small differences in syntax and semantics between the different languages. If we would just be doing Matlab, I think we would, and specifically if you're a beginner in programming, it's good to focus on procedural programming. What the more standard paradigm then is actually, in addition to procedural programming, object-oriented programming. Object-oriented programming. And programming looks somehow wrong. Programming? Programming. And this integrates data and functions, integration in objects, and or without the apostrophes. And this is, in a way, the standard paradigm how a lot of things are programmed these days. And the important thing is that Python is heavily object-oriented, in the sense that everything in Python is an object. In MATLAB, for example, you can do object-oriented programming, and you can also do only object-oriented programming in MATLAB if you want to, but it's not kind of the natural, or in a way, yeah, it's not the natural implementation of MATLAB. And for example, in C, you also have to, you can go without doing object-oriented programming, or you can do it, and most people then do it. The nice thing in terms of object-oriented programming is that you can define entities that both store data and functions that work on these data, and you can nicely capsule things that belong together in terms of modeling a real-world problem from other things. So from my personal perspective, for all these years that I did mainly experiments and data analysis, I used to capsule things, especially different data stuff. I use mainly what is called Matlab Structures, which is something like an object but without functions. The thing that really got me started on object-oriented programming, where I found it highly useful and actually the only possible way to do things, is if we do this agent-based behavioral modeling. So if you model in a simulation an agent interacting with a task and maybe you observing them, it's much more natural to use object-oriented programming, because essentially because if you model human cognition, you need some form of memory. So you need so human cognition doesn't work only based on functions. It also needs some memory. It needs so from trial to trial, for example, it needs to memorize what it has seen before. And if you then only focus on the functions, then you're somehow missing out, and the code really becomes a little bit annoying. So these days I'm using object-oriented programming a lot in our cognitive modeling. I find it sometimes, in terms for data analysis, I find object-oriented programming a little bit of overkill. So, for example, the SPM EG analysis code is object-oriented. Yeah, I don't know. I mean, whether you want the EG data to be kind of together with then functions that you can apply to it, I don't know. So I think for pure data analysis, I think procedural programming is fine. But for certain things, you definitely need object-oriented programming. And then the last thing is, of course, that essentially object-oriented programming should be a little bit cleaner in terms of capsulation and so on than procedural programming. So we will then, now that we are doing Python, we'll talk about in the beginning mainly procedural programming, but whenever you use Python, it will already be object-oriented, because all of Python is object-oriented. Okay, so now I'm actually done with what I wanted to do today in terms of telling you about some background in programming. The next time would then be to get started on programming in Python using Anaconda and Spider. So the reason why I am using Spider is because it looks a lot like Matlab, so I could easily switch to Python by using Spider. I think it's definitely not the only way you can use Python, so different editors, but this will be then the topic for the next session. And of course, for people who are not beginners and who are a little bit more advanced, you can also look into the script and think of whether you want to whether it's useful for you to look at this or not. For beginners, it's definitely useful what we will do next time, because it's kind of getting you started. Good. Any questions regarding what we've discussed in this session? So these kind of history of programming languages and these programming paradigms. If yes, please ask. Okay, I don't hear anyone saying anything, so I stop this here.